Oh, hello, and welcome back to this online section of H2P 112, Logic and Philosophy. My name is Dr. Richard Brown, and we will be continuing our discussion of natural deduction today. In previous discussions, we were talking about our conditional proof. And conditional proof is a technique whereby you have your premises and your conclusion, whatever that is. And if the conclusion is a hypothetical statement, let's say, then you perform conditional proof by performing an indentation, assuming something, and then showing that that leads to P, thereby saying that you've proved C horseshoe P. So indirect proof is a similar kind of proof technique. And indirect proof is really a way to formalize something that was familiar from our ordinary reasoning called reductio ad absurdum. So suppose that you wanted to prove that a certain thing was true, and necessarily the case, that it's an axiom or something like that. If you wanted to prove that, one way to do it is by assuming that it's false, and then showing that that leads to a contradiction. And if the assumption that something is false leads to a contradiction, then we can say that we have shown is that our assumption can't be true, and so we assume the opposite. So an indirect proof is accomplished in much the same way as conditional proof, whereby what you assume, though, is the negation of the thing that you want to prove. And so as usual, and of course we have all of our other 18 rules and our conditional proof if we need it. So let's just go ahead and jump right in and do an example here. So take the following argument, which comes from the book. Suppose we have A wedge B, and suppose that's horseshoed to C dot D. That's our first premise. And our second premise here is C horseshoe tilde D. And our conclusion is tilde A. Okay. Now, we could do a conditional proof, and you know, there is a way to use conditional proof to prove any conclusion that's valid, but we're going to here focus on indirect proof. So what we would do is assume the opposite of this, and of course the negation of it, and of course the negation of that is tilde A, but we can save ourselves a step here by sort of cheating and just assuming A. So what we do is we come and we indent our line, writing the new line down, and we write down the thing that we assume, and we say that we're assuming A for an indirect proof. So you write AIP, assumption for indirect proof. So now we write AIP, assumption for indirect proof. Now we can start working within our indented lines here and using our anything that we want. Now, of course, with a conditional proof, we were trying to start with the antecedent and show that we can get to the consequent. With an indirect proof, we're trying to start with the negation of the thing we want to prove and show that a contradiction results from that. So we can kind of see the beginnings of a contradiction here because we have tilde D here and we have D here. So if we could somehow get D and then also tilde D, then we could build our contradiction. So that seems like a good strategy. Now, how would we get that? Well, it seems like we could get that if we had this and we could do modus ponens. But we have A here, so we know how to get A wedge B. We can use our addition rule. Write down line 4, and we're at A wedge B, and we got that from line 1 by addition. We can add anything without changing the truth value as long as we know this is true, and we're assuming it is for our purposes of indirect proof. So now we have A wedge B, and we can use modus ponens to get C dot D. So we write down line 5, and we have C dot D, and we got that from lines 1 and 3 by modus ponens, as usual. So now, of course, we have to switch this. So let's go ahead and do that. We can write D dot C. Got that from line 5 by associativity. Now we can simplify. Line 7, we simplify. And we're doing that because we see that's sort of the way that we're going to get our contradiction here. So now we have D. We got that from line 6 by simplification. So that's interesting. Now, if we had C, we could get tilde D and be done. And we have C right here. So we can write down line 8. And this is our non-flipped form. We'll simplify that. And we get C from line 5 by simplification. Now, of course, you could have done these in either order. So you could have simplified this and then associativity switch that, and got D. It really doesn't matter. It's a stylistic choice. I did it that way. So now we have C, and line 2 together with that will give us tilde D, so we can write down line 9 here, and tilde D. And now we have our elements. We simply join them together to form a formal contradiction, D dot tilde D. And we got that from 7 and 9, 7, 9, by our conjunction rule. And this, of course, we got from 2 and 8 by modus ponens. Don't forget to keep track. Don't forget to keep track. So now we have D dot tilde D. That's a contradiction. We've done what we said we wanted to do. So we assumed A. That led us to a contradiction. And so now we can say that the negation of this is what's been shown. So we close off our proof. We write out our non-indented line here, and we write tilde A. And we got that for 3 through 10. 3 through 10 are indirect proof. So that's the procedure here for doing an indirect proof. And indirect proofs are very nice for showing various things. So let's go ahead and just look at one thing very quickly. So you may remember that if you take an argument form, so take modus ponens, P horseshoe Q, we have P, so therefore Q. We can write this as a conditional statement. So we can write P horseshoe Q, we can join all of the premises together, and we horseshoe that to the Q statement, to the conclusion. And now what we have here is called the Associated Conditional. So this kind of symbolizes modus ponens. Now what's interesting is if you take this sentence, so we have P horseshoe Q dot P horseshoe Q, and we know that this is a tautology. So let's show you what happens if we do an indirect proof without any premises. We're just going to assume, so we'll just indent line 1 here, and we're going to assume that it's that this sentence is false. So we're going to assume that it's not the case that P horseshoe Q dot P horseshoe Q. We're going to assume that for indirect proof. Okay? Because this is what we want to establish. So we simply assume that it's false and see what happens to that. So we can simply now use our rules that we have established. So we can write down line 2. Now notice that this is a negated conditional statement, but we don't have a rule that tells us what to do with this. So what we can do, though, of course, is use our material implication rule in here. And so we can write line 2, it's not the case, and write that, and we're going to say tilde P wedge Q, because that's what's equivalent to that. So we write tilde P horseshoe Q dot P, either that's not the case, wedge Q. And of course we still have our negation sign from here, so we simply worked inside here and we applied our implication rule to that. So now we have a negated dotted sign, and so we can use our De Morgan's rule, but of course we have a negated wedge sign operator, and so we can use our De Morgan's rule on that. And probably looking down the road, it's easier to do that second one first. So let's write down line 3 here, and we're going to use De Morgan's rule, moving this inside and changing the operator. So we move tilde, tilde, and then we have that, P horseshoe Q dot P. So we have tilde, tilde that, and this turns into a dot and a tilde Q. Okay, so that looks good now. We have a tilde Q around, and so it looks like we can build some kind of contradiction there. But of course, now we have this, and we know we can get rid of that using our double negation rule. So we write down line 4, and we simply write P horseshoe Q dot P, and that's going to be dotted to tilde Q. And we got that from line 3 by double negation. And we got this from line 2 by De Morgan's rule. Okay, so that's very exciting. So now we can simplify and we can get this. So we can write down line 5 and we'll write this down, P horseshoe Q dot P. And we got that from line 4 by simplification. So that's fantastic. Now we can associativity that, write down line 6, and that says P dot P horseshoe Q, and so that's fantastic, from lines 5 by associativity. And so now you can see where this is going. You simplify, you get line P, and you got that from 6 by simplification, and we have this here, so we can write down line 8, P horseshoe Q, and we got that from line 5 by simplification. Now we can write down Q on line 9, Q, because 7 and 8 is modus ponens. 7 and 8 is modus ponens. And so we have tilde Q here, we have Q here, we just need to flip this and simplify it. So we write down line 10, and we write tilde Q dot that, P horseshoe Q dot P, and we got that from line 4 by commutativity. Now we can simplify and get tilde Q. Now we have Q and tilde Q. We can write down line 12, and we write Q dot tilde Q, because lines 11 and 9 allow us to do that with our conjunction rule. And now we're done. So I'm running out of space, but we would close that off. We would come out and write on a non-indented line, and I'll simply do that up here since I don't have our own. We write on our non-indented line, line 13, and we can write this, and we say we got that because lines 1 through 12 are indirect proof. So what we've done now is to show that using indirect proof techniques, we can show that this is a valid argument. And notice that we did it with no premises. We started just with the assumption that this was false and nothing else, and our rules which allow us to manipulate the things. And that's a very interesting thing, that you can show that this follows from 0 premises. And typically, when we write that something follows from 0 premises, whether it's a proof to it, we often use the turnstile, this symbol here. And so we could write that this P horseshoe Q dot P horseshoe Q, that follows from no premises, and that we just demonstrated that using our techniques. Now, of course, we use the indirect proof technique, but we can also show that this follows, it is provable using our conditional proof technique, because what we can see is this is a conditional statement here. And so if we wanted to prove this, well, we would start in the normal way we do. We would indent our line, and we would assume this. So we would assume P horseshoe Q dot P, and we assume that for conditional proof. And we want to show that if you assume this, you get to Q using the rules that we have. So we can do that, and now we can simplify, and we get P horseshoe Q, and we got that from line 1 by simplification. And now we can flip it, line 3, P dot P horseshoe Q, and we got that from line 1 by associativity. And now line 4, we can do our modus ponens, and we have P horseshoe Q, and well, we want to do that, so we get simplify this and get our P from line 3 by simplification. Now we can finish this up. We have P horseshoe Q, we have P, so we can write down Q, and we can say that because 2 and 4 are modus ponens. And so now we've shown if you're assuming this, then you get to Q, and so we can come out here and write line 6, that's P horseshoe Q dot P does in fact horseshoe Q. So now, which of those proofs is the better proof? Well, they're both proofs. They both show that this is a valid argument. This one's simpler. There's only 6 lines. The conditional proof is pretty powerful here. But it's important to be able to realize that we showed in both cases that this follows from empty premises, and that there's a proof. This symbol is often meant to be that you can prove this. Now, if we introduce just a couple of new terminologies here, so if we say this versus this, so this is the notion of provability. This is the notion that it's valid, which is a semantic notion. So this is a syntactic notion. This is a semantic notion. And so we can formulate then two important properties of logical systems using these operators. So we want to be able to say that if there's a proof of P that exists, then P is valid. Okay, we want to be able to say that. And we also want to be able to say that P is valid, then there's some proof of P. And so these two properties are extremely important. These two properties are extremely important. So let me just write them up again. If there's a proof of P, then P is valid. That's the way that so that's our first statement. Our second statement here is just the opposite way. If P is valid, then there exists a proof of P. Okay, if P is valid. So this says that the things which are provable are valid, and the things which are valuable are provable. And if you have both of these, then your logic is sound and complete. And of course, what we want to be able to show is that every argument that's valid, there's a proof of it. And anything you can prove, you only prove the valid ones. There's no proofs that exist for invalid arguments, and there are no invalid arguments that there are proofs for. And of course, so we can look at this the other way. If you want to flip this around, this one right here says, well, if you can't prove that P, then P isn't valid. And the same here is if it's not valid, then you can't prove it. And those are the really important ones. Now, of course, the system that we're learning, natural deduction for propositional logic, is a sound and complete system. And that's what's interesting about it. Of course, now once you move up to the next level, we talk about predicate logic, things get a little bit more complicated. So let's go back and revisit the argument that we just looked at earlier. So that was, you may recall, A wedge B. And that was horseshoe to C dot D. And our second premise was C horseshoe tilde D. And our conclusion was tilde A. Now we could use a conditional, and what's what we did an indirect proof, but we could also use a conditional proof on this. And there's a technique, it's kind of trick, but it's fun, and so we'll play with it. So we start by assuming, just like an indirect proof, assume the negation of the thing that you're interested in. But this time we're going to do a conditional proof. I'm going to show you a technique which can be used here. And it relies on the same kind of technique that we were talking about before. We're going to assume for a conditional proof, we're going to get these contradictory statements. And then we're going to set up a disjunctive syllogism with those contradictory statements. So let's go ahead and derive our contradictory statements. We know how that's done. We just did it. So we write line 4. And we want to add B. So we write A wedge B. And we got that from line 3 by our addition rule. And now we do our modus ponens. So we write line 5. C dot D. And we got that from lines 1 and 4. 1 and 4 are modus ponens. Okay. So now we want to write down C, and we got that by line 5 by simplification. And line 7, D dot C, and we got that from line 5 by associativity. We need that, and so we want to go ahead and simplify and get D. Okay, so now we have C, and we can get tilde D. So line 6 and 2. Give us line 9, 2, and 6. I'm getting sloppy over here, but that's okay. We can write tilde D. We remember the steps from before. So now we have D and tilde D. Now remember, what we want to get is tilde A here. So we have our setup here. So now notice we have D and we have tilde D. So we can clearly do a maneuver here, and what we want to do is we want to get this. So let's go ahead and add it. So here's what we do. We write down line 10, and we're going to write D wedge tilde A, And we're going to say we got that from line 8 by our addition rule. So we added tilde A here. That's our conclusion. We added it because we can add anything. So we have this, so we add that. Okay. So now we have D wedge tilde A, and we have tilde D. So we can write down 11 here, and using our disjunctive syllogism, we can write tilde A. Okay. So that's very exciting. So we started with A. Now we got to tilde A. By the way, we got that from lines 9 and 10. 9 and 10 by disjunctive syllogism. So now we're done. We want to finish our conditional proof. We unindent our line. We write down line 12. What we've now proved is A horseshoe tilde A. Now that's a weird thing to prove. If it's not the case, if it's the case that A, then it's not the case that A horseshoe tilde A. It's a very strange thing to prove. But by material implication, let me just write that up here. By material implication, that's actually equivalent to tilde A wedge tilde A. And by our tautology rule, that's equivalent to tilde A. So notice what we did here. We want this conclusion, tilde A. So we've got to figure out how to get this, tilde A wedge tilde A, to use the tautology rule. So we do our conditional proof. We want to prove if A, then tilde A. So we want to prove if this, then that. And so we are able to do that. We can do that with any argument that we want to. With any argument that we want to. And so just by way of illustration, let's pick an argument from a previous chapter and re-examine it. And you know I like to do the translation exercises and all of that. So let's go ahead and do that. And this is number 4 from the book. And so we'll translate it and then we'll work on this. So the argument says, if astronauts spend long periods in zero gravity, only if calcium is reabsorbed in their bodies, then astronauts on a Mars voyage will arrive with brittle bones. If astronauts attempt a voyage to Mars only if they spend long periods in zero gravity, then astronauts on a Mars voyage will arrive with brittle bones. Therefore, astronauts on a Mars voyage will arrive with brittle bones. Okay, so we have Z for astronauts spend long periods in zero gravity. We have C for calcium is reabsorbed into their bodies. And we have B for they arrive with brittle bones. And we have V for attempt a voyage. Okay, so let's see. What's the conclusion here? That's obvious. It's therefore astronauts on a Mars voyage will arrive with brittle bones. So that's the conclusion. So let's go ahead and translate this. So what's our first premise here? It says, if astronauts spend long periods in zero gravity, only if calcium is reabsorbed in their bodies, then astronauts on a Mars voyage will arrive with brittle bones. Now notice that this is going to be 2 conditional statements, so it's going to be 2 horseshoes in there. This first sentence says, if astronauts spend long periods in zero gravity, only if calcium is reabsorbed in their body. So you have to remember, this is sort of getting us to refresh our memories about P only if Q, P if Q. So P only if Q really says if Q then P. P only if Q. If P then Q. I'm sorry, which one did I say? P only if Q really says if P then Q. P only if Q. And you know that because only if, when you think about what it says, what that really tells you is that that Q is a sufficient condition for P. Only if Q. So that's a sufficient condition. So if astronauts spend long periods in zero gravity, only if calcium, so that's going to be long periods in zero gravity, only if calcium is reabsorbed in their bodies, then they arrive with brittle bones. So there's our first premise. Z horseshoe C, in parentheses, horseshoe B. Second premise, if astronauts attempt a voyage to Mars only if they spend long periods in zero gravity. So astronauts attempt a voyage. So there we have V horseshoe long periods in zero G. So V horseshoe Z, that's going to be horseshoed to B with the brittle bones. And the conclusion here is, therefore, astronauts on a Mars voyage will arrive with brittle bones. Let me just double check that. ZCBV, ZCBV. So Z is astronauts spend long periods in zero gravity. C is calcium is reabsorbed in their bodies. B is astronauts on a Mars voyage will arrive with brittle bones. Therefore, B. Therefore, B. Okay, so now we have our argument written out. And of course, we have B here. So it seems like we could assume tilde B and do an indirect proof on this. So let's go ahead and try that out. So let's indent. We'll write line 3 here. And we're going to assume tilde B. Assumption for indirect proof. We're going to try to show that it leads to a contradiction and therefore conclude this. Okay, so we've assumed that for our indirect proof, and now we can do some stuff with it because this looks like a modus tollens here. So we can write down line 4 and get this tilde Z horseshoe C, and we got that because lines 3 and 1 are modus tollens. Okay. So that's all very nice. Now we can use our implication rule here, tilde, and that's going to be tilde Z wedge C. And we got that from line 4 by implication. Now we can use our De Morgan's rule. We can write line 6, and that's going to be tilde Z dot tilde C. Okay? And we got that from line 5 by De Morgan's rule. You can get rid of that. Line 7 is going to just be Z dot tilde C, and that's from line 6 by double negation. So that's great. So we can see what we can do with Z and C, or tilde C, but first let's work on what we have up here. So we have modus tollens again we can do, and we can do line 8 here, and write tilde U horseshoe Z, tilde U horseshoe Z, because lines 2 and 3 are modus tollens again. And we can do the same procedure here. So we write down line 9, tilde U, wedge, Z. Got that from line 8 by implication. And line 10, De Morgan's rule, tilde V, dot tilde Z. Okay, now we see the contradiction, Z and tilde Z. Right there, and that's all very nice, but we got that from line 9 by De Morgan's rule. Now we want to flip that, so write lines 11, tilde Z, and yeah, we could use our thing, double negation, and get rid of that, but there's no real need to do that right now. It's not going to help us. Dot tilde V, and we got that from line 10 by associativity. Now we can write line 12, tilde Z, from line 11 by simplification. We can write down line 13, Z, from line 7 by simplification. Now we have to join them to make the formal contradiction, and it must be in this order, Z dot tilde Z, because we defined the contradiction in that terms, and we did that by conjunction. Now we have our contradiction, so we can say that assuming tilde B leads us to a contradiction, and so we're allowed to infer then line 15 the negation of that, so we would write tilde B, and we got that from line 3 through 14, indirect proof, and then to finish it off, write line 16, and that's B. We got that from double negation on line 15. So now notice what we've done here is to derive the contradictions and then show that doesn't work. Now, of course, what we could do if we wanted to is we could do a conditional proof on this as well, and we would do it in exactly the same way that we did before. So let's just go ahead and try that. So suppose that we weren't doing an indirect proof, but assumption for conditional proof. So what we're going to show is we're going to try to show tilde B, horseshoe B. Okay, we're going to try to show that you can get to B by assuming tilde B. And we do that in the same way, first of all, by writing out all the stuff that we have written out. And we want this contradiction just like we have it here. But we're not going to conjoin them. We're not going to conjoin them because remember, we want B. So now we can write down line 14 here. We can take this Z and we can add B to it. Because we can add whatever we want. So we got that by adding it to 13. Now we have our disjunctive syllogism. And we can say Z wedge B tilde Z. So we're allowed to write B. And we got that from 12 and 14, which are disjunctive syllogism. Now we've discharged our assumption for conditional proof. And we can come out here. I'll just write it up here. Line 16. Excuse me. We'll write up here, line 16, tilde B, horseshoe B. So now we're done. We write line 17, tilde B, wedge B, from line 16 by implication. And line 18, B, wedge B, got rid of that, from 17 by double negation. And then we can write line 19, B, because that's from 18 by our tautology rule. So you could use either one. You could use either one. Now in this case, indirect proofs happen to be a little bit simpler and easier to do, but neither one of them is more technically correct than the other. Okay, and so there's indirect proof. Now the last thing that we should say, and I won't go through examples, though I could if we want to, is that you can use these within the scope of the other techniques as well. So if you want to do indirect proof inside another indirect proof, you can. If you want to do an indirect proof inside a conditional proof, you can. The only thing to keep in mind is that once you've discharged your assumptions, everything in that area is off limits. Okay.